Okay, so I seem to have forgotten to teach you a particular chapter from our textbook, and that is on the Claisen condensation and acylation of enolates at carbon. So I just want to give a quick overview of what you need to do. This is not actually a very difficult chapter at all, and I'm just going to explain to you what we expect you to know in this course. Let me just start first by reminding you of what we do know. We've looked at enolates in a whole host of different forms as our basic enolate structure over there, and we've looked at many different ways of making either an enolate like this or the different enol equivalents of this. So for instance, we could make an enolate using lithium diisopropylamide, LDA, and we get just a naked enolate like this. We could do it via an enolate. We could, where we would have something like this, minus some R group over there, maybe it's a T-butyl. We have an enolate. We could have an enamine. Generally, there's some sort of cyclic amine that has been made from there. And then lastly, we have the silyl enol ethers. So we've looked at all of these, where we would use these and how we would make them. And then we've looked at the different types of reactions that we do with these enolates. In other words, what is the coupling partner? These acting as nucleophiles. And what are the electrophiles that we use? Well, the electrophiles that we've looked at have been sort of our alkyl halides reagents, and we've also looked at the aldehydes, all right, the aldol type reactions. So we know the reactions of those, and then Prof. Anotolu has been looking at the unsaturated systems that look a little bit like that. The acylation or reactions is where we're using an electrophile that looks like this, X. All right, now X can be a whole host of things. Often X, particularly in organic chemistry, we refer to as a halide. In this case, I'm going to just say that we can use other things. It's going to act as a leaving group, but the flavor that this comes in is either a halide like chlorine, or it is an ester. So let me give an example of one of the most basic examples of an acylation. It's a classic example of the Claisen reaction itself. This is when we take just ethyl acetate. All right, that's the solvent ethyl acetate. And if we stir this up with some ethoxide base, what happens is we can deprotonate there and form our enolate. Now, just remember, of course, that ethoxide is not a particularly strong base, and the protons over there are not very acidic. And so when we enolize this, we're only forming a small amount of the enolate. So anyway, we do that, we form our very small, low concentration of this enolate, and we can do that mechanism. And then this enolate over here, this ester enolate, can react with the starting material because it is also a good electrophile, this ester carbon. And if we follow through in the mechanism, what's going to happen is it's going to kick in, that's going to go there, and we're going to kick out like that. So what does that product look like? Minus OT, new bond, carbon, and OET. Looks like that. Now, this tetrahedral intermediate over here, the negative charge can kick back in, and of course breaking this bond over here would send us back to our starting material. However, and that's fully possible, that can happen. However, if it kicks out an OET like that, the product that we end up with is that. And of course, we released one molecule of OET minus, and OET minus is of course a base. And what it's going to do, and this is the important thing out of this whole reaction, is that now this product that we've made over here, which is ethyl acetoacetic acid, which we've seen being used in our enolate chemistry, the protons here are now a whole lot more acidic, and they can be fully deprotonated by the ethoxide. And so the ethoxide is going to come in, we're going to deprotonate and form our an enolate, which is now very stable. So we'll draw it out. Okay, so this is the most important thing about this reaction and why this reaction works, because you see these things that I've shown you before are all reversible. But it's at this point over here, in fact it's really bad to put that in there because it's not going to go back. At this point over here, once we form this enolate, this is now stable and nothing more can happen with this. And it's because the ethoxide that's released is basic enough to pick up this proton. So this reaction ends up just going to the product over here. You don't get any of the reversal reactions happening. Again, the key point here is to just note that what we've done is we've effectively taken okay, once we finish the reaction, we work it up, we end up with this OET. And what's effectively happened, if we just go think backwards in the reaction, okay, going back that way, is that we formed this bond over here. And this thing over here, putting on a carbonyl onto this carbon over here, is effectively what is known as the acylation of a carbon. All right, which is what the Claisen reaction does and what these electrophiles do. Well, that's the basic setup that I've shown you over here, but actually this can happen in many different forms. For instance, say we had this compound here that we wanted to make. Say we wanted to make this compound over here. We ask ourselves, well, how would we make this compound? Well, when we do a disconnection, when we think backwards, we recognize that actually we know how to acylate at a carbon. This carbon here is next door to a carbonyl. So we could break that bond and we could start off with something that looked like that and something that looked like this, but we need to put a leaving group on it, so we're going to put something on there. We'll write an X at the moment, and we could get those two things to react. What's better to use there is actually just a chlorine. An acid chloride is quite a reactive intermediate, and under the conditions that you've learned, the different ways of making enolates, the acid chloride is going to be an absolutely perfect partner for this reaction to occur. So now you're actually left with a whole host of different ways of taking getting these two things to react. We could form our lithium enolate with LDA and then add this, and we would get this reaction. We could make a silyl enol ether. It's a great one to use, and then we could add this and we get this react. We could use the aza enolate, and we can use the enamines. In fact, the enamines are often preferred in the literature, but it's not a critical thing to use only one of those. And then, so hopefully you can see that's not too difficult. You're going to get examples in your tutorial. Just two things which sort of electrophiles which come out of this, which are important to remember. The one is diethyl carbonate, okay, diethyl carbonate. All right, diethyl carbonate, you can see this is an ester, and when it reacts, or when the nucleophile, your enolate, reacts with that, this goes out, comes back in, kicks out an OET. So what you're going to be doing is you're going to be putting an ester onto a carbonyl over there. All right, so in other words, the product would be an ester at that point. If you're not sure what I've just said, go and do some arrow pushing and just see where you get to and what it looks like. And then the other one is this, which is ethyl formate. Once again, you can see this is a type of an ester. Here we've just got a hydrogen over there. The interesting thing is that, of course, if we do this type of reaction, what we're going to get, because this is going to be the leaving group, is we're going to be putting on a formyl group. In other words, an aldehyde will be attached to, in this example, if this is the nucleophile over there. So these are two interesting ones that we need to look at. All right, so Prof. Enolates is going to cover some of this in your lectures and just build a bit more on this. And you're also going to get a tutorial on Friday. The amount of work that's necessary in the exam for this is not very hectic. I'm actually confident that even without these lectures, you would have been able to give the correct answers, because you guys have been doing pretty well and have been studying hard. So keep up the good work. I look forward to marking your exams.